Okay, um, this is a second consideration of a problem with pistons, a cylinder that's fitted with a piston, and furthermore, the cylinder has installed a set of stops. Um, what we know about this configuration is that the initial total volume is 4 meters cubed, and that at the level of the stops, the enclosed volume is about 8.9 meters cubed. Furthermore, we know that there are 10 kilograms of water contained within this system. So furthermore, we know that the weight of the piston is such and the external pressure is such that the pressure inside the system is 400 kPa, and that the piston is free to move until it hits the stops. And so the pressure will be constant until such time as the piston hits the stops. I guess I can denote this V1 and V2 because it's stated as part of the problem that we're going to add heat to this system, which will cause the steam to vaporize and to raise the piston, and that we're going to continue to add heat until the piston hits the stops, and that's going to be state 2. And then furthermore, additional heat will be added to this system until the final temperature is 800 degrees Celsius. So the questions that follow are, what are the states T2, what's the temperature at T2 when it hits the stops, and what is the final pressure? And since we've talked a little about boundary movement work, we now ask the question, how much work is done in going from 1 to 2, and how much work is done in going from 2 to 3? And as well, I guess I'm going to add the question here, what is the initial quality or the initial temperature? And I don't mean that you have a free choice of which one to give, but if it's in the two-phase region, give the quality, and if it's in the superheated region, give the temperature. So this exercise is a little more about understanding the phase or phases that are present based on some information that we might know about the system. So recall that we need to know 2 property coordinates for each state in order to identify the phase or phases that are present for each state. All right, well, begin at the beginning. We need to know 2 properties about the first state. So for state 1, we know the pressure. So we know 1 property coordinate. What other property do we know? Well, we know the total volume, but that won't really help us directly. We also know the mass in the system. And so if we think about state 1, we know that the specific volume 1 is the total volume divided by the mass, and that's going to be 0.4 meters cubed per kilogram. So now just looking at this last question I inserted here, which we'll consider the first question, we need to determine which phase or phases are present when we know the pressure and the specific volume. My advice always, when we know either P or T and one of the intensive properties, is to go first to the saturation tables, the saturated water tables, and determine if the value of specific volume falls within the range of that for the two-phase mixture. I'm going to go ahead and start a schematic over here that I hope will help us understand what's going on here. So temperature, volume might look like that. I don't know where 400 kPa is, but I'm going to show it right here. And the first question is where is state 1? So to analyze that, we'll look at VF and VG at the 400 kPa and try to see where does that fall. So I have a set of tables which I'm not able to show you. They're not printed out. But if I look in the pressure table for water at 400 kPa, I find that VG is 0.46242. And since the specific volume that is given is less than that, we know it's to the left of this saturated vapor line. But furthermore, since we can quickly see that the specific volume of the saturated liquid is very small, like 0.001 something, we recognize that the V1 is somewhere in this region. So we can calculate X1 from the specific volume and so we've got 0.40 minus 0.001084 divided by and with a little help I might be able to calculate that. Let's see. I get this number to be 8647, 0.8647 is the initial quality. And so if we needed to, we could use that initial quality to calculate the internal energy or the enthalpy of this first state if we needed to. Okay, now the question is, as we add heat to this and it's going to hit the stops, where is this second state? So the pressure is going to remain constant. And I guess the question immediately becomes, does the phase change continue into the superheated region, or does it hit the stops before it becomes saturated vapor? We can note that when it hits the stops, the specific volume is going to be equal to 0.8900, where this is just the volume at the stops divided by the mass in the system. So I'm going to have, when it hits the stops, the specific volume is equal to 0.89. Well, we have already discovered that VG at 400 is 0.46242, so I can conclude immediately that at the stops, it is going to hit the stops. The state at the stops is in the superheated region because this V is much greater than this V. So we'll come out here somewhere like that. Okay, so the question is now, what is the temperature? What is the temperature at the stops? How will I find that? Well, I know that the pressure is 400 kPa. I also know it's in the superheated region because I reasoned that out from this expansion part. And so state 2 is defined by the property coordinates P2 equals 400 kPa and specific volume 2 equals 8900. So if I go into the superheated tables, I can hopefully identify a place where that's matched up or where I can interpolate. So in my superheated table, and I hope it's the same as yours, but in my superheated table at 500 degrees C, and 400 kPa, specific volume is 0.88936. Which is very close to 0.8900. I mean, it's 0.8894. So the difference is 0.0006. So it's pretty close. We could interpolate, but I think our effort would be more or less wasted. We could just say that T2 is approximately 500 degrees C, because that's basically right in the table. Okay, so that answers the question about T2. What is the final pressure then, P3? Well, we do need to recognize that once the piston is at the stops, then the volume is going to remain constant and the specific volume is going to remain constant. So V2 equals V3, and this final pressure, the final temperature is given as 800 degrees. And so we can see that the state 3 is fixed by the property coordinates T3 equals 800 and V3 is equal to V2 is equal to 0.8900. So we know it's in the superheated region from the sketch, and we know the temperature and the specific volume. Again, it's a search in the superheated tables going across the tables where the temperature is fixed, and we're looking for a specific volume of 0.89 at 800 degrees C. So in my tables, I find the pressure to fall between 500 kPa and 600 kPa, and then I'm going to need to interpolate. In other words, a specific volume at 800 C and 500 kPa is 98966, and the pressure there is 500. The specific volume I'm looking for, and then the specific volume at 600 kPa, 82457, and that's at 600. And so again, I want to set this up using my differences to interpolate, and I'll say that 8900 minus 0.98966 divided by 0.82457 minus 0.98966. That's the same as P3 minus 500 divided by 600 minus 500, or 100. Again, this quantity is what I will call my fraction, and that fraction would be key to interpolation for any other properties that I need to know between those two states. So let me see if I can put a number on that fraction. The fraction I get to be 0.6037, and when I multiply that times 100 and add to it 500, I get that P3 is 560.4. Okay, so let's see how we're doing on the questions. The initial state, the second state, the third state are all known, so we can find any of the properties that we need: internal energy, enthalpy, find them in the tables using these property coordinates that we have identified for each state. Now we're asked to find the work done in the first process, 1 to 2, and the work done in the second process, 2 to 3. So for the work from 1 to 2, it's just going to be the integral of P dV, and we can write that as the mass times the integral of P dV. This is just going to turn out to be, because the pressure is constant, and we recognize this result, it's a constant pressure process, we can calculate it exactly this way. So we have 10 kilograms, and the pressure we have is 400 kilopascals, and the specific volume change is, at the stops, it's 0.89. At the initial state, it's 0.40. And we need to be careful of the units here. The kilograms go away, which is great, but we've got kilopascals and meters cubed, so 1 kilopascal is 1 kilonewton per meter squared. And when I get rid of those, I find out that I end up with kilonewton meters, and 1 kilonewton meter is 1 kilojoule. So my answer will surface in kilojoules if I can work it out here. Let's see what I've got. So 0.89 minus 0.4 times 400 times 10 equals 1,960 kilojoules. We were also asked to find the work done from 2 to 3. Was the integral P dV, but since there's no volume change in 2 to 3, remember our state 2 to 3 is just going from along a constant specific volume or constant volume line. So since there's no volume change, there can be no work done. Okay. So that's everything for us. I think we're really just about ready to use the first law of thermodynamics to calculate some of these other energy quantities, but we'll leave it off this example for now. But to summarize, we need to know 2 property coordinates for each state, and many times we need to use the path from one state to the next to connect those states and to identify the properties at the subsequent state. For example, here we had to use the fact that P1 equals P2 and that we knew the specific volume 2 that allowed us to find the second state. And likewise, we had to use the fact that V2 equals V3 to connect to the given information about state 3, so that we now have property coordinates for state 3. And finally, we had evaluation of boundary movement work for these 2 simple processes, and we found that the work in the first process, 1 to 2, about 1.96 megajoules, and in the second process, no work is done since the volume is held constant.